Okay, 1988 BC 44. Which of the following series converge? The first series, which is an alternating series because of the -1 to the n plus first power, is going to converge by the alternating series test. And just to review briefly, the alternating series test has three basic criteria. First, the series must strictly alternate, which this does because of the n plus 1 exponent. For odd powered exponents, you're going to get a negative term, and for even powered exponents, you'll get a positive term. Second, the terms must decrease in value. A sub n plus 1 has to be less than a sub n, so the successive terms must be smaller in value than preceding or previous terms. Now, we would have to use some formal method to prove this, but intuitively you can see that when n is equal to 1, you're going to get 1/3. When n is equal to 2, you're going to get 1/5, 1/7, etc. And so these definitely decrease in value. Third, the limit as n approaches infinity of the nth term has to be 0, and it is here. 1 over 2n plus 1. As n goes to infinity, the denominator will be infinitely large, the numerator is 1, and so it approaches a limit of 0. Alright, so that one is going to converge by the alternating series test. The second series is a little bit more problematic. It looks like it's a geometric because of the 3 over 2 to the nth power. But the 1 over n term is changing each time. So we're not simply multiplying the previous terms by 3 over 2 to get to the next term. So this is technically not a geometric series, although intuitively I would think that it diverges because that common ratio 3 over 2 is greater than 1, but we can't leave it at that. So I'm going to have to do I'm going to try a ratio test on this. And so the ratio test might look something like this. Limit as n approaches infinity. We need the n plus first term, and I want to write this so that it's not so complicated. Let's see, I would get 1 over n plus 1 times 3 to the n plus 1 over 2 to the n plus 1. Then we're going to multiply that by the reciprocal. I guess this is where it gets kind of a little bit more difficult. We would have n times 2 to the n over 3 to the n. I think that would be the reciprocal of the nth term. And we should have absolute values here. And so what I might do here is to line these up. Limit as n approaches infinity of n over n plus 1. And I know that that has a limit of 1. Second of all, let's do the 3 to the n plus 1 over 3 to the n, and that is going to have a limit of 3 to the first, or 3. Finally, we'd have 2 to the n over 2 to the n plus 1, and that is going to have a limit of 1/2. And so that would give us equal to 1 times 3 times 1/2, which is 3/2. And since that is greater than 1, diverges by the ratio test. For the ratio test, for it to converge by the ratio test, that limit has to be less than 1. Alright, finally, let's go on to the third series here. Now this series is a classic example of where to use the integral test. And so the integral test, we would set up a corresponding integral, or an integral that corresponds to that infinite series. And it might look something like this, with limits of 2 to infinity. And here you would use u, do a u substitution with u is equal to natural log of x, so that du is 1 over x dx, which we have right in the problem. We'll swap that out. And so would like to swap out the limits of integration. Since u is natural log of x, natural log of infinity is still going to give me infinity. And when u is equal to 2, that would give me, when x is equal to 2, the u value would be natural log of 2. So we would then have limit from natural log of 2 to infinity of 1 over u du, which turns out to be natural log of the absolute value of x from 2 to infinity. And when we take the natural log of infinity, that grows without bound, and so that does not exist, or it diverges. And what the integral test tells us is that if the corresponding integral diverges, then the series also diverges. So let's go back and see what we have here. We have the first one converges, the second one diverges, and the third diverges, leaving us with option A, 1 only. And that'll do it for this video. So this is a great problem. It's a little bit more time consuming than others. However, we're using the alternating series test, we're using the ratio test, and we're using the integral test all in one problem here. And so it's a great way to practice some of the important convergence tests that we need for the BC test.